So this is a class on infrared spectroscopy. So if I just take you to your textbook, guys. This is chapter 2.7, so we're starting on page 203. So if you couple the reading of the textbook and doing the questions in the textbook, along with what I do in this PowerPoint, I'm going to do the theory of this topic, and then I'm also going to do the some past paper questions at the end. Okay, there's plenty of opportunity though in the exercises in the chapter for you to have a go at some new questions on your own and check those with the answers. Okay. What I would say, this is quite a short topic, so it's not too bad, but it will take into account all of the sort of the aspects of organic chemistry we've done so far. So let's get stuck into it and see what infrared spectroscopy is actually about. Well, the first thing I'd say is it's a high-tech analytical technique. You've already done some technique or some chemical experiments which will allow you to identify functional groups in organic chemistry. So, for example, if I said to you, how would you identify a tertiary alcohol from maybe a primary or a secondary alcohol, you might say you would warm it with acidified potassium dichromate. The primary or secondary will, of course, turn orange to green, whereas the other, the tertiary one, will just remain orange. So that's a chemical test. If I said to you, how would you differentiate between an alkane and an alkene, you might say, well, we'll add a few drops of bromine water to both, give them a good shake. The alkene will decolorize the bromine water from orange to colourless and give you two layers, whereas the alkane will give you two layers but will not decolorize it, it will remain orange. Okay, so that's another chemical test. Okay, high-tech analytical techniques are dry tests. We don't need other chemicals, and we need, the beauty of them is we need extraordinarily tiny amounts of the chemical in order to carry out the test. So let's have a look at what this is actually all about. So within infrared spectroscopy, it depends really on the covalent bond within these molecules, of which there are many, vibrating a bit like springs, and they vibrate at a particular frequency. So for example, if I hit certain bonds with certain amounts of radiation, infrared radiation, okay, they will vibrate. Other bonds will do nothing. And we use the fact that they vibrate at different frequencies, different energies of infrared spectrum or infrared radiation to actually identify what bonds are in a molecule. And if I can start to identify what bonds are in a molecule, I can start to identify that molecule. So the movement of these bonds when I apply or hit them with infrared radiation, they carry out some stretching and some bending. Okay. So if we look at sort of a bit of an animation of it here, you can see what happens. Okay, so bonds, they're not rigid and static structures within a molecule. They have the ability to absorb energy, and therefore if I apply infrared radiation, the bonds in these covalent molecules that we're studying have the ability to absorb that radiation. Okay, so bond frequencies are similar to those of infrared radiation frequencies, and that's why we use infrared radiation, of course, in this analytical technique. And when they interact with the bonds, they will interact differently depending on the bonds that I have there. Okay. So if we look at infrared radiation, in terms of the electromagnetic spectrum and in terms of wavelength, the electromagnetic spectrum, it lies between our microwaves and our visible radiation. Okay, so it's pretty small wavelength radiation here. Okay, and these are the radiations in which our bonds are carbon-carbon double bonds, our carbon-oxygen bonds, our OH bonds, our C-double-O bonds, okay, our C-single bond C bonds, our CH bonds. These are the radiations within which those particular bonds happen to absorb radiation, and we use the amount of radiation that is absorbed within this region, to work out what bonds are in a molecule. And if I can work out what bonds are in a molecule, hopefully I can start to piece information together and work out what is a molecule. Now that might be coupled with some other information in the question as well. Okay, so let's sort of have a look at what happens here. So in infrared radiation, we will take our sample, okay, our organic sample, and we will pass through it all frequencies of infrared radiation. So if I go back to here, the frequencies that we're talking about are the frequencies, okay, in terms of hertz. From there, it's probably about 10 to the 10 hertz, okay, roughly, till about, what's that, about 10 to the 14 hertz, okay. So that's the frequencies of radiation that we will pass through our sample, okay. And our sample will absorb, so let's take this area here, okay. Our sample in this area here has absorbed all of the frequencies of those particular radiations there. So all of those ones there, I think, have been absorbed. Some other ones are partially absorbed. So for example, this one, this one, this one, and some of them are not absorbed at all. So we can build up a pattern of the radiation, the infrared radiation that is absorbed completely or partially or not at all. And from that we can start to build up a picture of the bonds that are in that organic molecule. And once we can build up the bonds that are in the organic molecule, okay, we can start to identify it. So this is kind of the fingerprint, if you like. Okay, that's kind of the fingerprint of the organic molecule. Now a computer will piece together the information and tell us what bonds are in there, okay? Although we get very simplified ones, traces at AS level and A level, which we can use to identify bonds present. We'll go through that today. Okay, so we look at the percentage of infrared radiation transmitted and the frequency at which that infrared radiation is, and we take all that information and we plot it, and this is the type of trace here then that we will get. Okay, so we have percentage transmitting of the infrared radiation there. Okay, and we have the wave number. Okay, and the wave number is basically related to the frequency of that infrared radiation. We don't need to worry too much about it, but we will pretty much treat it as frequency of that infrared radiation. So what can we see here? Well, we can see this area here, okay, there is basically zero transmittance. So that's kind of, there is none of this radiation, whatever it is, in this frequency getting through. So that's kind of like this region here. If we look up here, well then all of this infrared radiation in this region here is getting through. So all of that is getting through. And then some other ones is just partially absorbing it, and that's partially getting through. And it is this picture that we build up that allows us then to identify the molecules that we have. Now, very importantly, in AS chemistry, okay, so from about there down, okay, what we will see, okay, from about where I am, I've lost my pen, sorry, okay, from about there, that 1500 down, this allows us to identify functional groups, this region here. Now I'm not going to go into really why that is, okay. From 1500 up, this is called the fingerprint region. Okay, that allows us to identify really the structure of a molecule beyond the functional group. So for example, if I had, let's say, ethanol, and I had propanol, they both have the same functional group. So from 1500 down, their traces would look the same. And you might go, well, that's not much point in that, because that doesn't allow me to tell whether it's propanol or ethanol. Well, then from 1500 in this direction, okay, that is the fingerprint region, and that will allow me to tell whether it is propanol or ethanol. Okay, so from here, from our 1500 up, we're looking at functional groups just. From 1500 down, we're looking at whether it is the propan-1-ol or propan-2-ol or ethanol or whatever. Okay? Now, at AS level, you'll be glad to hear, we only have to work really from 1500 up. Okay, but you do need to know a little bit about what the sort of the fingerprint reading will actually tell me. So they might ask you a question like, well, if you've got a trace and you're not sure if it's ethanol or propanol, how would you actually decide? And you would talk there about the fact that you would use the fingerprint region. Right, so let's look at analysing these these infrared specs. So we use this and we use a table, and you'll get a table, you'll see one come up here in a minute, you'll see it on probably in the back of your periodic table at A level. You'll get an infrared correlation table, okay, and you use it, okay, with the numbers on it to look for the presence of particular absorbances, but also the absence of particular absorbances. That is equally as important, looking for functional groups, basically peaks and therefore functional groups that are not there, okay? And we will use those then to work out, as we said in the next line there, what functional groups and bonds are actually there. So let's have a look at a couple of simple ones. It doesn't go into too much detail in AS chemistry for these. So for example, on a trace, if we have a peak at about 1700, 1750, that tells me I have a carbon-oxygen double bond. In fact, I'll tell you what I'll do. I'll bring this table up here for you first, and we'll talk through it. This is a very complicated looking table, and you won't get one with as much detail as we have on the board now. But, so for example, if I have a peak at 1680, okay, so if you go back to what we had there on the first slide, we have percentage transmittance, and we basically have frequency. It's called wave number, but we'll call it frequency just for simplicity's purposes here. Okay, so if I was to have, let's say, 1680 to 1750, my trace was sort of like that, if you like. I had a peak there. That would tell me I've got a carbon-oxygen double bond. Okay, a good strong peak, which is what I have there. Now, it tells you that that's a carbon-oxygen double bond, but it could be an aldehyde, could be a ketone, could be in a carboxylic acid, could be in an ester. We haven't done esters, so we're not worried too much about them. So it's not that region is not specific to that bond. Okay, or the bond is not specific to that molecule. So it could actually be three different molecules here. It could be an aldehyde, could be a ketone, could be a carboxylic or oic acid. Okay, so you would have to couple that with the presence or absence of other peaks to try and work out exactly what it was. So if we had an OH group, for example, let's say a hydrogen bonding, an OH group in a carboxylic acid is between 2,500 and 3,000. So for example, if I went up here and I have a peak, so there's 2,500, there's 3,000. Let's say I have another peak, it's medium broad. If you look out there, it says medium broad. So let's say I have another peak in that region there. Okay? Well, therefore, I can probably say that that's an OH of an oic acid. So now I'm starting to build up a picture of what this molecule is. I have a C double bond O down here. Okay, so I have a C double bond O there, and I have an OH there. I put both those together, and I should know now that I have a carboxylic acid. Okay, if I had this peak here on the right at 1750, and I didn't have a peak here, well then I can tell that it's not a carboxylic acid because there's no OH in it. It must be either an aldehyde or a ketone. Okay, so hopefully you're starting to pick up. Right, so let's look at these three peaks, or these two peaks here. I can have a COO or I can have a OH, okay, at this region here. So we're looking for bond identification. So these could be aldehydes, ketones, carboxylic acids for all of those. So let's look at our table. We've got a trace, so let's say we were given a trace by an examiner in here, and we went through it and we looked at all of our peaks. Okay, sorry about my artwork. And we found in the first one we had an OH group, but no C double bond O. So what functional group? You maybe want to pause the video here and try and work these three conclusions out yourself. Well, if I have that, that means it must be an alcohol. Okay, I have no C double O, I've only an OH. Okay, so it's not a carboxylic acid, it has to be an alcohol. In the next one, I have no OH, but I do have a C double bond O. Well, that has to be an aldehyde or a ketone. Okay. And on the next one, I have an OH and the C double bond O, kind of like the one I did in the previous slide. That's a carboxylic acid. Okay, so we can read off our correlation table, read off our trace first of all, then read off our correlation table, and then start to deduce what we have got in terms of functional groups. So that's the type of correlation table you'll get in your exam there. I think that's one I've just taken out of a exam paper. Okay, so you'll see here you have two different peaks for OHs, one on an alcohol and a phenol, but wouldn't worry about that until A2, okay, or one in a carboxylic acid. The carboxylic acid one is a very, very broad peak. When we talk about broad peaks, we talk about peaks like this here, so very broad peak. This is a very strong and sharp peak here, so that is a broad, weak peak. Okay, this is a strong and sharp peak. Okay, you'll see the other OH group for alcohols is broad, so it's not as broad as the so it might be something like this. Okay, for this one it's broad. Okay, so very broad, sharp, okay, and broad. You'll recognize these better as you sort of go along. I think any of the ones that are here that are not referenced to being broad or anything are really all pretty sharp peaks. Okay, so let's look at that one. Okay, it might be a good idea actually, guys, if you took a photograph of that on your phone or something before you went and did these, or I think it's maybe on the back of your periodic tables anyway. It'll certainly be in your textbook. If you look on page, I think certainly page 207 of your textbook, you'll find some of these. Okay, probably all the ones you need for A level, to be honest with you. And also there's also a little chart on page 206 as well, which will probably give you all that you need. And there's another one on page 208 as well. Now sometimes these figures vary slightly from question or paper to paper, so sometimes they don't always correlate exactly if you're using a chart or a graph or a table from one source and a question from a different one. Anyway, let's have a look at this. Okay, so clearly we have an OH, we have a broad peak, okay, fairly broad peak there from 3000 to 35. Okay, what do we not have, which is important? We don't have that C double bond O there. Okay, we don't have that big sharp peak running down there. Okay, and that tells us we have an alcohol. Okay, we can't tell that it's ethanol, we can just tell it's an alcohol. To work out that it's ethanol, we would have to employ this region, this fingerprint region here. Okay, but that's kind of beyond where we need to be. Let's look at this one. This one should be, so maybe a good idea, if you think you've got this sort of cracked, you maybe want to pause the video, and whenever I bring up a new slide and or a new trace, and see if you can work out what the functional group is. So in this one, we've definitely got a big C double O there, that's at about 1750. This time we don't have an OH group, so this has to be an aldehyde or a ketone. Again, we can't tell what it is. Okay, so it is indeed propanone. Okay, but again, you would have to be analysing that. Okay, that region there. Let's look at this one. Okay, so we definitely have an OH. We definitely have no C double bond O. So again, this is another alcohol. This one's in fact propan 1-ol. And again, if you go back to the ethanol from a couple of slides ago, you'll see that the 1500 down the fingerprint region is different in the two. If I just flick back to it very quickly, maybe you can sort of see. Okay, so they're not massively different, but they are different. Okay, let's look at this one then. Okay, so we have a really broad OH here. Okay, it's running the whole way from about 2.5 up to about 3.5. Okay, 2,500 to 3,500. That's an OH, really broad. Okay, and a C double O as well. So there we go. That tells us that we this time have a carboxylic acid. We've got both of those functional groups. And it's good that you start to, so you can see the OH group there compared to OH group in an alcohol. So OH group in an alcohol here is broad. OH group in a carboxylic acid here is very broad. Okay, Then we have this funny little one here, which sometimes people get a little bit confused at it being an OH, okay, for a carboxylic acid. But you see a little double prong on it, and it's actually a double pronged NH. So just be a little cautious of that. Here's another little double pronged one here sitting down at about 3000, which again causes people difficulty. This is a CH. Now, it's pretty much a useless peak because in every organic molecule you'll get a CH. Okay, you'll see a little remnant of it there in that one. Okay, let's see if it's in this next one. You'll see it there in that one, again a CH. No, it's of no use to us. Okay, you'll see a little remnant of it there, again in that one. Okay, so CH is in pretty much every single organic molecule at S level and A level, so it's always going to be there. Okay, so if we have a look at that one, sorry, okay, you can see there's my NH, that's my CH, okay, that's my NH, and that's my CH, okay, so all I know in this is that I have an NH. You might know there's an NH2 group in it, okay, because we did, that's if you remember back in haloalkanes, we did amines, okay. Again, you wouldn't know that it had a 3 carbon chain on it. Okay, have a look at this one, see if you can work out what it is. Okay, so there's not much going on. This, it looks a bit OH-y, but it's not big enough, okay, for our OH, or if you remember our alcohol or carboxylic acid OHs, they were of much more significance than that. That's just CH bonding, okay. This is below 1500, so we don't worry about it, and that's my C double bond O. So all you would know is it was an aldehyde or ketone. Again, you can't tell anything more than that. Okay, have a look at that one. Okay, so here again we have a C double bond O. We have a bit of a sneaky one here because we have a C single bond O down there, which is not really on S spec. I use this more for the A2 gid when they're doing. Okay, so this is not big enough to be OH. This is just a CH that we've already had. So the only bond you would pick out there to S chemistry would be that one. That's the C single bond O there, which was the other one, but again, not on the AS specification. Okay, have a look at that one. Okay, bit of a sneaky one to put in here. So here we have the NH, the double pronged NH, which sometimes can look like a COH, but remember it's that double pronged ending on it. And then down here we have our C double O. So in terms of you guys, you should know that that's in there and that the NH is in there. Okay, those are the two functional groups you would be expected to pick out. That's actually a compound called an amide. Okay, it's not on your spec, but you can read the trace and work out that that's there and work out that that's there. Okay, pause the video, have a look at that one. Okay, so let's see where we are. This bit of peaking here, not significant enough to be an OH. This is not high enough to be an NH, it's just simply CH, that double pronged CH. Here we have C double bond O at about 1680, 1750-ish. So all we've got is C double bond O. Okay, have a look at that one. Should be starting to maybe recognize some of these peaks a bit better now. Okay, so here hopefully we can pick up big broad OH of an alcohol, of a carboxylic acid, sorry, and then our C double bond O just to affirm that that's what we've got. So there we go, carboxylic acid. This one. Okay, so we have here, hopefully you're getting to see these now, OH, and it's of course an alcohol. We have no, we don't have that big, deep C double O, big sharp C double O. Some of you might have picked up here that you have from earlier that C single bond O, which is of course, you would know in an alcohol here. So you might have seen that. Okay, so we've got a few questions here that you can do. Okay, so how would you use infrared spec to tell the difference between a sample of butanol and butanoic acid? Okay, you need to refer to peaks that are present and absent. So maybe you want to pause the video, do these, and then come back and see my answers. So I'm just going to do the answers all now, and it'd be a good idea if you just pause that video and then came back and checked. Okay, so how would we do this? Tell the difference between sample of butanol. Right, well, very simply, this will have a broad peak. Okay, and that broad peak will be at about 3.2 to 3.5. We have to quote values. Okay, butanoic acid will have a very broad peak. Okay, and that will be at about 2.5 to 3.3. I'm just quoting these numbers out of your textbook. Okay, but this will also have another peak, which will be at about 1680 to 1750. That'll be a very sharp peak. Okay, so that's how you would do it. Next one, a sample of ethanol is thought to be impure. How would you use infrared spec to verify if the impurities will exist? Well, you basically take this sample and you overlay it, or you compare it, okay, with a trace of pure ethanol. Okay, and if this one has more peaks, okay, so what you'd be looking for, and quote this, if it has more peaks than the one of pure ethanol, then there's impurities in it. Okay, a pharmacologist thought they had developed a new drug. How could you use infrared spec to confirm they had developed a new drug? Well, very simple. You would, the trace of the new drug doesn't previously exist. So all of these traces are previously exist. So all of these traces are held in a computer base. Alright? If you've made a whole new drug, well then that trace isn't going to happen. It's not going to be anywhere. Okay, number 4, student was making some propanoic acid by oxidizing propan-1-ol. How could the student use infrared spec to confirm the reaction had gone to completion? Again, you should refer to peaks present and peaks absent, as well as specific ranges. Well, if we look at propan-1-ol, okay, 1, 2, 3, OH group there, when we oxidize it, it goes to propanoic acid. So how can we use it to prove this reaction has gone to total completion? In other words, there's none of this left. Well, this is kind of a bit like the one we have at the start. We start off here with a broad peak in our trace at 3.2 to 3.5 roughly. Okay, at the end, it's important that we show this has now gone. But what has it been replaced with? It's been replaced by a very broad peak at 2.5 to 3.3. Okay, it has been replaced by another peak, a sharp peak. Okay, so just this one, that is this one here. The other one is the sharp peak at 1680 to roughly 17.5. Okay, so that's showing that oxidation has completely gone. The other place that this infrared spec is used, it's been used in space travel, where little space buggies go out into planets and take samples of the rock or the soil in a planet and give an analysis of that, up to what sort of elements and what sort of compounds are in that rock. So it's used fairly extensively from that perspective as well. Right, we're going to have a look at a few questions here, past paper questions. Right, so the purity of a thing called alpha terpenoid, okay, obtained, it may be determined by infrared spec. Okay, so this is our alpha terpenoid here. Explain why the molecule absorbs infrared radiation producing an infrared spec. Well, why does it absorb? Well, that's going right back to the first couple of slides that we did at the start, and that's because the covalent bonds, okay, have the ability to absorb infrared radiation. Okay, so specifically the covalent bonds absorb that infrared radiation. Okay, Right, identify the peaks by stating the range. So we've got to state the range of wave numbers in the spectrum which correspond to the functional groups in the molecule. Right, let's get the functional groups in the molecule first. We've got alcohol, we've got carbon-carbon double bond. So dead easy, identify the peaks. Okay, well we would get a peak at 1620, and again I'm quoting these out of the textbook, to that, and that is equivalent to a carbon-carbon double bond, 1 mark, very easy. We would get another peak, and make sure we pick the right OH group for an alcohol, not a carboxylic acid, so 3230 to 3550, that's the OH group, second mark, dead easy. There's no other functional groups in that, that's it all done. Okay. Some people say, I remember marking this, some people wrote that there was a CH group in there at 2850 to 3300. That is marked wrong. That's not a functional group. It asks you specifically for a functional group. That might be a peak that you get, but it's not a functional group. Okay, explain how we would use the infrared spec to determine that the sample of alpha terpenoid was pure and free of all impurities. Well, if it's pure, the trace of the sample will match exactly. Okay, so there will be no more or no less or no fewer peaks than the trace of the pure alpha terpenoid. Okay, so that's it. It would just be exactly the same. In all ways, all peaks would be exactly the same. Right, ibuprofen can be formed by the reaction below. Okay, state the suitable reagents and conditions. So we're getting into a bit more chemistry this time. Okay, so let's do that first. Suitable reagents and conditions. Well, we've got to find out what are we doing. Well, I've been a bit devious here because we kind of flipped the product 180 degrees to try and confuse you here a little bit. But really all we're doing is we're taking this and we're turning it into that. So that is a primary alcohol going to carboxylic acid. You should know that that is acidified potassium dichromate and it is heat. Okay, so there's your answer to A and B. How would you obtain the product from the reaction? Well, you would eventually, that should be heat under reflux actually, I suppose. You would obtain it by distillation. Now we don't know its boiling point, so we can't quote that. State how the infrared spec could be used to show the reaction going to completion. Kind of like the question we had earlier here. Okay, originally we will have a peak at for our alcohol at 3230 roughly to 3550. Okay, now if it's going to completion, that peak is completely gone. It has been replaced by the carboxylic acid COO there at 1680 to 1750, and you will also now have COH group of carboxylic acid, a big broad one, okay, at 25 to 3000. Okay, so just saying that probably don't need this, but that's very sharp and that's very broad. Okay, so hopefully you're starting to get the idea as to what's going on here. Right, a step in synthesis of ibuprofen, so in other words the way in which you make it, suggests a reactant which could be used in this step. Okay, so if you look at it, what we've got here, that is the same as that. So we're asking really, what might you add to here, okay, to make this reactant into the product? Well, let's see what we've got. We've got a carbon, and a carbon. So we have 1, 2, 3 carbons there, okay, and we've an OH group on the end of it. So it's probably, you're looking for something like propan 1-ol. Okay, so I think that's really all they're asking you kind of to work out. how the infrared spec to be shown the reaction has been successful. Okay, well, if it has been successful, you've now got an OH group here. That's the only difference really in terms of the functional group that you will get. So if it's been successful, you now have a peak that is present at 3230 to 3550. Okay, wave number. Okay, so it's 3230 to 3550. Okay, because you now have an alcohol group. Nothing else in the molecule will change. Okay, and there's no other functional groups in this region that you've added on. Okay, so cinnamaldehyde can be hydrogenated with nickel at 170 degrees Celsius. Draw the structure and state how IR spec can be used to show the reaction has gone to completion. Right, well, the product is the double bond breaks, becomes single, and I now have a hydrogen here and a hydrogen here. Okay, how do we show that that reaction has been successful? Well, the only thing that's changed is that my carbon-carbon double bond, which is at about 1620 to 1680, was present at the start, and at the end that's completely gone. There's no point in talking about this peak here, okay, that's the sort of a 1700 one, because it doesn't change. It's still there at the start and it's there at the end. Okay, so that's the peak that has gone. Okay, alright, so hopefully that allows you guys then to go and have a go at the questions and the reading in chapter. I'll just remind you what it is, even going back to the start. So it's chapter 2.7. There's some questions in your class notes as well. Okay, so I will attach the answer to the class notes to the Firefly task, and I'll attach the answers to these. And if there's any queries or questions, I'll expect obviously that you will come to me with them.